Hello everyone, welcome to another Watch Me Do Math video. In today's video I'm going to be talking about a vectors question from Further Pure Maths. This is from a past paper, summer 2016, June 2016, paper 1. And the reason that I am doing this question is because a viewer wrote in, Nikhil Kanade, and he was asking me specifically to do these kinds of vectors questions that have about a 1 in 2 chance of coming up in any given year, I suppose. And they involve finding some sort of simultaneous equation out of the relationships between two vectors, and that's something I'll get into later. Basically, you may know these as lambda mu style questions, and in this video I'm going to be approaching one in as much detail as I possibly can to explain to you how to do it. So you've got this diagram here. OA, this vector from O to A, is vector A. OB, this vector from O to B, this entire thing is vector B. And OD, from O to D, which is clearly D being on the same line as OB, all 3 points are collinear, is 2 over 3B. So that's just that this segment OD, 2 over 3B, is twice that of DB, which by implication is 1 over 3B. They also mention that the point E divides AD in the ratio 2 to 3. That implies that there is an earlier segment, AE, which is 2 parts of it, and a later segment, ED, which is 3 parts of it. So if we ever find the vector AD, then AE will be 2/5 of that, and ED will be 3/5 of that. So let's approach the first part of the question. It says, find as simplified expressions in terms of A and B, AD, OE, and BE. So let's begin with AD. We've already established that D is 2/3 of the way between O and B. So we can say that the position vector OD is 2 over 3B, as that's something given to us. At the same time, OA we already know is the vector A. So if we're looking for the vector from A to D, you are going backwards along the vector OA and then forwards along the vector OD. So overall, the journey you're making, AD, is minus OA plus OD, or overall, minus A plus 2 over 3B. And that is our simplified expression in terms of A and B. That's AD. So that's part A, I, completed. Now we move on to the next part. Find OE in terms of A and B. Now, one approach we can take to finding OE, this actually took me a little bit of thinking, is although it may be tempting to think directly from O to E, is there any vector we can make use of? You want to just find any journey of vectors you already know that goes from O to E. And that journey is firstly O to A, and then A to E, because we know AE is going to be 2/5 of AD, as I discussed earlier. So if you want to put that all in writing, A2, you have, from this diagram, OA followed by AE. That is, your target is OE is equal to OA plus 2 over 5 AD, as we are given the information that AE is 2/5 of AD. So we just make clear that this is the segment AE, or the vector AE. So if we substitute what we know into this equation about OA and AD, we get OE is the vector A plus 2/5 of AD. So 2 over 5 times minus A plus 2 over 3B. And if we expand this all out, we get A minus 2 over 5A plus 4 over 15B. Or, to simplify, this becomes overall 3 over 5A plus 4 over 15B. And that's OE in a simplified form in terms of A and B. Now we move on to the next part of the question, vector BE. So we want to find a journey from B to E. Well, similarly, now that we know OE through OAE, and we know OB is just the vector B, we can go from B to E first by traveling to O, then to E, or in more fundamental terms, from B to O to A to E, because we know AE, we know OA, and we know BO very easily. So to write this all down, the form we can take is that BE is minus OE, or minus OB, that is, going from B to O, plus OE, going from O to E via A. So this is minus the vector B, plus 3 over 5A, plus 4 over 15B. Or, to simplify, this is minus 1 plus 4 over 15. Well, if you take away 4 fifteenths, there are 11 fifteenths left. 11 over 15b plus 3 over 5a. And note how they ask for just a simplified form in terms of b and a. It doesn't really matter what order you put a and b in, because we just know that they are two arbitrary, non-parallel, non-zero vectors, right? So anyway, this is an acceptable form for the end of the question. BE is this vector in terms of a and b. So just to recap what we've done, to find AD, we first found the route from O to D through the information given in the question, that OD is this vector, a route from O to A, gone backwards from A to O, then from O to D. In finding the next part of the question, vector OE, we used the information that E was a certain part of the way between A and D, as stated in the question, used our new knowledge of AD to find this vector AE, which is helpful for us because we can add it to the vector OA, which is the other part of the journey aside from AE, when going from O to E. So we found OA plus AE is whatever OE is. And then to find BE, we took our newfound information of OE and applied it by taking the additional journey from B to O before going to E, because that entire journey is equivalent to just a journey from B to E in vector terms. So hopefully that explains how to do the first part of this question, which is 5 marks. Honestly, something that is a fair number of marks for just the first part of a vector question like this. But anyway, let's continue. The point F lies on OA such that OF is lambda OA and F, E, and B are collinear. Okay, so how do we interpret this question? These 3 points are collinear. That suggests that F must be on the line that goes through both E and B. Or you could also say something else like B must be on the line that goes through F and E. But remember, E and B are the only ones that exist right now. They're the only ones on the diagram right now. So a way we can treat this is by extending the line EB. So it goes up this way, down this way. This whole line EB is where F is going to be. And so F is somewhere along this line. What other information can we use? Well, we know that F lies on OA, on this line here. That means F must be this point here. OF is lambda OA, meaning that this is lambda, whereas this is 1 minus lambda. It's a lambda to 1 minus lambda ratio, so that the whole thing is 1 OA. And that's basically the information we're given. And we want to find the value of lambda. This is where the most difficult technique for people facing these kinds of questions for the first time comes up, the lambda mu kind of technique. What happens is that there usually is a point of interest that you're trying to find some vector towards, and that point of interest in most lambda mu questions will be a point that is on the intersection of 2 lines that you were dealing with earlier in the question. Now the thing is, they usually aren't explicit about the fact that you need to use a lambda mu technique, but this question actually is sort of semi-explicit about that fact. It says find the value of lambda. Now, of course, there is a way to find lambda without actually resorting to the lambda mu technique, without actually constructing some simultaneous equations, but you don't actually need to do that because there is a I would actually say, simpler way and more useful, more applicable to a wider range of questions in further pure maths IGCSE disqualification, if you learn how to use this lambda mu technique. So the fact that it's on the intersection of two lines that you already know, or sort of two lines that are extensions of lines that you're already familiar with, allows you to construct two equations. The first equation is one that's given to us. OF is lambda OA. OF is lambda of the A vector times the A vector. But the second equation is not so obvious. So the first equation comes from that first diagonal line OFA that we're already dealing with. But the second equation comes from the diagonal line FEB. And the key thing to note here is that we can treat FB as an extension of EB. So if you have this vector EB and you multiplied it by a certain amount, mu, where mu is going to be greater than 1, so say this section is like one part of it, and this entire thing is mu times EB. So FB is mu EB. That will usually give you a second equation, because you can go from what you know about FB and what you know about OB, just the fact that it's the regular vector B, to an additional expression for OF in terms of mu and the A vector and the B vector. So I've talked a lot about this, but let's actually try it, because that's the most helpful thing you can do when approaching a new problem-solving technique. So remember, there are two equations we want to create. The first one is quite explicit about which one we're making. OF is lambda OA. So let's write that down. For part B, equation 1 is OF is lambda times OA. Or if you want to put this in simplified form, OF is lambda times the A vector. Now we want to make a second equation that is based off the fact that FB is an extension of EB. So BF, for instance, I'm going to use the direction B to F because it's the same direction as B to E along that line EB. BF is mu BE. And you might be asking, how does this actually help us? Well, it helps us because we can convert this information, as I said earlier, to information about OF. Because to get from B to F, you must first go from B to O, and then from O to F. They are equivalent journeys. The vectors that represent those journeys, those displacements, will be the same. So OF is minus OB, going from B to O, plus BF, or OF is minus B plus mu BE. And we want to gather a little more information about this, and it's helpful to us that we've actually found an expression for BE in terms of B and A already. So let's write that out. BE is 11 over 15 times the B vector plus 3 over 5 times the A vector. OF equals minus B, going from B to O, and then hang on. Oh, wait, give me a moment. I think I may have done something wrong. Okay, I've unpaused the recording. I figured out what I did wrong. This OF should be positive OB plus BF, because you are going from O to B and then from B to F, not in another direction. Because the whole journey OF can go through B, rather than it being in some other configuration. I confused myself by thinking it was in this order from B to O to F, but that's not really relevant to the question. Okay, so putting that aside, just correcting that error by making all of these B vectors positive, as we're looking at positive OB, journey from O to B, we substitute in the information we know about BE. So it's plus B vector plus mu times 11 over 15 B plus 3 over 5 A. And For the next part of the question, I would recommend that you simplify both of the two equations that you might have for a single position vector, because that's ultimately what you're doing. You're finding two expressions for the same vector, one in terms of lambda and one in terms of mu, each expression coming from a different line that you're dealing with. My first expression coming from the line OFA, that's given in the question. My second expression coming from the line FEB, but remember that you won't always be given one of the lines in the question. You must identify yourself the two lines you're dealing with. You find these two expressions for OF in different terms, and then you use the fact that there is a unique vector in terms of A and B that represents every vector to construct two equations. So again, that's a bit of an abstract thing that I'm saying, but I'm going to explain to you what I mean in a moment. But for the time being, let's just simplify this in terms of something A plus something B form. So you have 3 over 5 mu A plus 1 plus 11 over 15 mu B is OF. And this is the same as lambda A plus 0B. And that's the key insight you've gained from making these two equations. The fact that OF, if I may zoom in on this a little bit, OF is this vector in terms of mu, and this vector in terms of A and B. Now let's talk about two-dimensional vectors for a second. So we know that A and B are not parallel. And the nice thing about that means that if you have an expression for any vector in terms of A and B, suppose this is some vector we're looking at in terms of A and B, and say this is A and this is B. If you want this vector in terms of A and B, there will always be a specific number of A's and a specific number of B's that always corresponds to one point. There is no other unique combination of A's and B's that is equal to the same vector. Because if you try to use a different number of A's, then the outcome of the vector would always be skewed in the sort of A axis, and the outcome of the vector would always be skewed in the sort of B axis if you try to use a different number of B's. So you have the knowledge that if you've got two expressions for the same vector in terms of A and B, you know that these numbers are going to be exactly the same, because this expression of a vector in terms of some number of A's and some number of B's is unique in 2 dimensions at least. And as long as A and B are not the same vector, like they're not pointing the same way. I know that I've done this with perpendicular vectors, which might make it harder to trust my point because it's not a whole case. Of course, this is an illustrative example that can also be helped by thinking about A and B in terms of the unit vectors I and j that refer to points in the coordinate plane. Like, for instance, if you're looking at a single point on the coordinate plane in terms of I and j, that position vector is going to have a unique number of i's and a unique number of j's to it when you decompose it into those two parts, right? But even if they're not perpendicular, say A was like this and B was like this, you would have some line of B's of any amount. So say this is just a line of B's that you can reach from a certain A point. This line of B's would shift in the A axis until you finally meet the point you're looking for. So there's a specific number of B's from the A axis, and there's a specific number of A's from the B axis. So suppose the B axis was over here. Sorry, just catching my words. If you have a unique vector x, and a and b are two non-parallel vectors, this amount of a will never change because there is only one amount of a that this x can be decomposed into. And at the same time, there's only one amount of b that this x can be decomposed into. There's only one amount of b that can be extracted from this x. Because, as I said, if you are going to change the number of b's, then a will never actually hit this starting point that you want, this desired beginning of the vector. And if you change the number of b's, or if you change the number of a's, then b will never hit this sort of ending point that you want of the vector. And so the key point I'm really trying to drive home here with these diagrams is that for every vector, there is only one unique representation in terms of two vectors that is possible, as long as those two vectors are not parallel. In a similar way to how, in terms of I and j, the Cartesian coordinate plane basis vectors, there is only one expression in terms of I and j that describes each point there. It's just that instead of I and j as our basic units, we're using some arbitrary units that the question has provided for us, a and b. So what do we do with this information? And by the way, there's a whole nother video on basis vectors and about this concept I'm going to link in the description. What do we do with this information now that I've talked to you about this amazing property of two-dimensional vectors? Well, we use this property to construct a simultaneous equation because we know this number, this coefficient that multiplies a, must be the same in both cases. For instance, 3 over 5 mu must equal lambda because the amount of a's in the vector OF is a constant. It doesn't change. There's only one possible answer. And in the same way, the number of b's in the vector OF is constant. It won't change. There's only one possible number of b's that could possibly make up both OF. So 1 plus 11 over 15 mu is equal to 0. And these are our two simultaneous equations that we want to solve and finally get a value for lambda. So if 1 plus 11 over 15 mu is 0, then 1 is minus 11 over 15 mu multiplied by 15 divided by minus 11, and you get minus 15 over 11 equals mu. And at the same time, 3 over 5 mu is lambda, or lambda is 3 over 5 mu if you prefer. So lambda is 3 over 5 times minus 15 over 11. You cancel the 5s, you get this 3 here. It's equal to minus 9 over 11. Wait a minute, that does not sound right. Hang on. Okay, I figured out what happened. It's this 11 over 15b down here. This needs to be a negative. Okay, so if we put this back in our working here, this becomes 1 minus 11 over 15 mu, and 1 minus 11 over 15 mu puts this as a positive, puts this as a positive, puts this as a positive, and puts this as a positive. And overall, lambda is 9 over 11. So I'm just going to quickly consult the mark scheme to make sure that's correct. Alright, I've consulted the mark scheme. It is correct. Lambda is 9 over 11. And that's how we do it. That's how we do the lambda mu technique for problem solving. So now I'm going to move on to the final part of this question. The area of triangle OFB is 5 square units. Find the area of triangle OAD. Give your answer in the form P over Q, where P and Q are integers. Alright, so let me just clear the board. Okay, now we focus on part C. The area of triangle OFB is 5 square units. Find the area of triangle OAD. This is a fairly tough question. I'm going to have to think about it for a bit. So first, I'm going to talk about what I've drawn onto the diagram here. We knew from the previous question that the extension of BE to BF was by a factor of 15 over 11. So that means 11 parts was here and 4 parts are here. In the same way, because OF is 9/11ths of OA, 9 parts of that side are here and 2 parts of that side are here. And I think the most relevant thing to our question as well is the fact that this is a 2-to-1 ratio because OD is 2 over 3 of OB. So ultimately, this is a kind of half base times height question. You want to see by what amount the base is modified, and you want to see by what amount the height has been modified. Alright, I'm just back from a toilet break, and I've thought about this question, and I have an explanation for you all. So, the thing is, we start with a formula for the area of the triangle OFB. It's 5 square units, right? So, we know that F is going to be some height above OB. Let's call that height H, okay? So, or we'll call this height HF, is the height of F above OB. And there is also a base to the triangle OBF, and that is, of course, the side OB itself. So, the base is the side OB. Well, let's just call this H for the height, for instance. So we know that 5 is going to be half BH, is the area of the triangle OFB, where B is that length of the vector OB, and H is the height of F above OB. Or, in other words, you can also express this as the length of the altitude from F to OB. So I'm just going to write that down. Right, so we know from the question that the area of this original triangle, half BH, is equal to 5, or rather, BH is equal to 10. Now the thing is, when you move to the triangle OAD, you are sort of transforming the base and the height of the triangle. So, how does this work? What do I mean by this? Well, when you go to the triangle OAD, let's start with an intermediate triangle OFD. When you go to the triangle OFD, you may be able to see where this is going. The base of this triangle decreases by a factor of 2/3 from OB, because OD is naturally 2/3 as long as OB. So this new base, I'm going to call B apostrophe, or B prime, which is the base of the new triangle OAD, is equal to 2 over 3 times B, or the original base. At the same time, we can use this fact to find the area of this intermediate triangle ODF. So the area of the triangle ODF is equal to half times the new base times the old height. Now, if we put this in terms of the old base and old height using this equation here, we can get an area for this triangle, for instance. And I'd like to emphasize that this is just an intermediate step, because once I explain the whole thing, you would probably be able to make the logical jumps in your head needed to answer this question. So B prime, the new base, in terms of the old base, 2 over 3 times the old base, you get area is half times 2 over 3 times B times H, or A is, well, the 2's cancel out, 1/3 BH. The area of the triangle ODF is 10 over 3. And this is, like, after you see this, you may be able to expect or sort of predict what comes next in the solving of this question. And if you predicted that we're going to try and find a transformation of this old height into this new height, or what multiplication factor you need to go from the old height to the new height, then you'd be correct, because that's what we're going to do. But you may be confused as to how we do it, because we just know that there is some arbitrary height here, and we don't know how to get to the height we want of the triangle OAD here. So even though we've managed to deal with the base component of half base times height, going from, what triangle was that originally? Going from OFB to OFD, or even OAD, even though we don't know the height yet, we don't know how to deal with the height component. And one thing that helps is thinking of this in terms of similar shapes. So you see this little triangle here. I'm going to call the foot of this altitude x and the foot of this altitude y. Okay, these are the points where F lowers to OD and A lowers to OD and a perpendicular line to OD. So this triangle OFX has got some certain angle between OA and OD, right? And it's also got a right angle here because that's what we decided. It's just the line that goes straight down from F to OD. And finally, that means this angle is going to be the same as well. It doesn't really matter what it is. And at the same time, we have another triangle where suppose this is OF, the length OF, and we know because of what we found out in the previous question, what we found out about lambda, that the side OA is 11/9 as long as OF. Well, like strictly speaking, we found out that F was 9/11 as long as OA, but they mean the same thing. Those statements carry the same information. So this side here, from OA to the new x, or OAY, this side is going to be 11/9 OF. So what that suggests is that if you have some original height here, then the new height here, by the principles of similar shapes, is going to be scaled up by the same ratio of 11/9. So the new height is 11/9 times the old height, simply because it's a similar triangle to the old one that we're dealing with here. Another way of thinking about it is that you could break down this vector OF into a horizontal and a vertical component. So if there was some expression for OF in terms of I, the base horizontal vector, and J, the base vertical vector, say OF equals MI plus NJ, then since we know that the new vector from O to A is 11/9 times OF, or that is OA is 11/9 MI plus 11/9 NJ. This is just an example, by the way, so don't be worried if you're kind of lost here, but I'm trying to make the point that because you can break these vectors down into horizontal and vertical components, you know that if the whole vector is scaled up by 11/9, then the horizontal component must be scaled up by 11/9, and the vertical component must also be scaled up by 11/9. And this works no matter the two vectors you're decomposing the vector into. Both component vectors, or all component vectors in fact, if you're decomposing into more than two, are going to scale up by the same multiplier. So this new height is 11/9 times the old height. So finally, we want the triangle area, we want the area of triangle OAD, where h prime is 11/9, h is the height of OAD in terms of just square units. But we only know square units in terms of the old b and the old h. So, given that the area is half times b prime h prime, the new b and the new h, we get the area is half times 2/3 times the old base times 9/11 times the new height. And that's, cancel that, cancel this 9 with a 3 to get 3/11, you get area is 3/11 base times height, which is, since base times height is 10, 30/11 units squared. Now I'm just going to check with the mark scheme to see if that's correct. I've just checked and it's wrong. This is meant to be 11/9h. So you get overall 1/2. The 2 still cancel out. It's 11/9, 11/27 base times height. And since base times height is 10, the old base times the old height is 10, you get an answer of 110/27 units squared. And that is the area of the new triangle. So, in essence, the way I'd like you guys to think about it, because it's the kind of question that with enough experience you can get so fast at that it's basically free, because it involves sort of manipulating the triangle in your head. You're so familiar with these ratios already that because you've worked with them throughout the entire question, that should be easy enough to just imagine this triangle OFB in your head, and then imagine it morphing into OFD, and correspondingly decrease the area by the amount, so 5 times 2 over 3. So you just write area OFD equals 5 times 2 over 3 equals 10 over 3, and then imagine it growing to fill the entire space up to A, and multiplying by a factor of 11 over 9. So you take your 55 over 9, you take your 10 over 3 from the previous question, times it, multiply it by the 11 over 9 from this part of the thinking, and you get your final answer, 110 over 27, with very little effort indeed. So over time, the more of these sort of triangle-related vector, lambda, mu style questions you do, the better you will get at finding the areas like this in the part C of this question. So that's all I have for now. If you enjoyed this video and it helps you understand the question better, please be sure to leave a comment, share this video with your friends, or like it, save it to your playlists, whatever. And if you have requests for questions or topics you'd like me to cover on this channel, email me or leave a comment. Email me at watchmedomath@gmail.com, or the email address in my About page, which is the same thing. So until the next video, thank you for watching.